result for a problem in both of these areas. So let's start with dynamic graphs. So what do you mean by a dynamic graph? Well, the graph is changing, and how is it changing? Well, at each step, I can add an edge to the graph or delete an edge from the graph. Okay, and you have to maintain some solution of graph theoretic or optimization problem more efficiently than recomputing from scratch. So we can always, after each update step, recompute from scratch. Okay, so we want to do something better than that. And what are the type of changes? Well, it's called incremental if only insertions are allowed, decremental if only deletions of edges are allowed, or fully dynamic if both insertions and deletions are allowed. And how do you judge your algorithm? Well, it's normally judged based on the update time. So after I have made a change, how much time do you take to update your solution? Okay, so this is about dynamic graphs. And there have been a lot of problems in dynamic graph. I have listed some of them. So one of them is connectivity. One of the first problems. So you have a dynamic graph, and a query can, edges can be inserted or deleted, and then a query can come, is S connected to T? And you have to say yes or no. Now, how much time will it take? You can obviously do a BFS from S every time, and that would take order m time if there are m edges in the graph currently, but can you do it in polylog time? Okay, in the dynamic setting. So this is one of the famous problem, connectivity. Then there is this single source shortest path. So you have a single source, you have to maintain the shortest path from this source to all the other places. Alternate shortest path, again, generalization of single source, strongly connected component, minimal spanning tree, and recently even topological solving. So I'm not going to all of this. I will concentrate on matching. That is the second talk, as I said. So a matching in a graph is a set of edges L such that no two edges in the matching share a common endpoint. Like in this particular graph, AG and DH, they form a matching. It may not be a maximum matching, but it's a matching. Okay. And I will use a very simple result. This was not a simple result, but the consequence of this result is this simple result. It says that we can find 1 plus epsilon approximate matching in a static unweighted graph in this much time, m by epsilon. Okay. So their algorithm, they found a maximum matching in m square root of n time, but their algorithm takes square root n phases. That's why there are the running time is m square root n. But if you terminate after 1 by epsilon step, you can show that the size of matching is greater than the maximum matching divided by 1 by epsilon. That's why it is 1 plus epsilon approximate, and this is the running time. So we'll use this. And this is the problem. You have to maintain approximate matching in a dynamic graph. It's a fully dynamic graph. And this all I've already told you, at each update step, edge would be added or deleted from the graph, and you have to compute matching quickly. And this is what we prove. This is a fairly old result. So what we say is we can maintain 1 plus epsilon approximate matching in roughly order square root of n time. Okay, and it's a pretty simple result. As I said, both the results are pretty simple in this talk. So this is the key idea. So can we find a smaller subgraph G prime of G such that the size of maximum matching in G prime is same as the size of maximum matching in G? Okay, so I want to find a smaller subgraph of G. Okay, so the maximum matching in both the subgraphs are actually same. And the answer is yes, if you give me an approximate vertex over the graph. Okay, so we will see the proof of this. But let's see how do you find an approximate vertex cover, because this is a dynamic graph. You have to actually maintain an approximate vertex cover also. Okay. So assume that you have an Oracle access to the vertex cover V cover at every update step. And this assumption is due to this result. This is the result by Neyman and Solomon. And they say that you can actually maintain a 3/2 approximate maximum approximate matching in a dynamic graph. Now let me tell you how to find a cover using matching. Well, you take both the vertex in the matching, and that is your vertex cover. So you take all the matched edges and both the vertices which are form a matching, that is the vertex cover. If if you start with a maximal matching, well, maximal matching means a matching which is not contained in any other matching. Well, it is too approximate, and that is a vertex cover. That will give you a vertex cover. And you can show that this matching, which Newman and Solomon are maintaining, is also a maximal matching. Okay, though it is 3 by 2 approximate, it's better than 2 approximate, but it is a maximal matching, and this will give you a vertex cover. The running time of this particular algorithm is square root of m, which is roughly same as what we are also doing. So we can use this particular algorithm. Okay, and so it will report all the vertices in the matching as this vertex cover.
Just to understand, this will give you a 3 times optimal vertex cover or this?
So, well, we just want 3. Oh, okay, you are saying it will be 3 times optimal.
No, I'm just checking. So, it's more than a matching.
So, look, even if it is a maximum matching, what is the size of vertex cover that you can claim for that? Actually, there is nothing that you can claim when you start with a maximum matching.
At least 2 times.
At least
2 approximately. Taking both the endpoints is a 2 approximate.
Yeah, so and maximal matching is also at 2 times. So this will be also So that's what I'm saying. There is actually no difference between maximal matching and maximal matching in this case. Okay. So this is a graph G prime that I'm maintaining. So what I'll do is include all the edges which are within the vertex cover. So all these edges which are within the vertex cover, this is my vertex cover. And for each vertex in the vertex cover, I will include at most V cover plus 1 neighbors outside the vertex cover. Okay? And this is my core graph, and I am saying this is my G prime. And what I will show is that the size of maximum matching in this core graph, which is G prime, is same as the size of maximum matching in G. And let's prove this, it's pretty simple. So among all the maximum matching in G, let M prime be the one that uses maximum number of edges in my core graph, G prime. So you include all these edges which are inside the vertex cover, which both the endpoints are in the vertex cover in your core graph. And for each vertex U in the vertex cover, you include at most V cover plus 1 neighbors outside the vertex cover. Okay. Oh, pardon? All these neighbors must be distinct. So this is a simple graph.
Not across vertices.
No. These, you can have a neighbor from here to here. This edge can be. Okay, so, but these neighbors are distinct. So among all the maximum matchings in G, let M prime be the one that uses the maximum number of edges in my core graph. Okay. So the picture may look something like this. So these red edges are the matching edges in M prime. Okay. So one thing to note that a matching edge cannot be here because one of the endpoint is in the vertex cover. Okay. So if all the edges in M prime are also in my core graph, then I'm done. There's nothing to be done. So let's assume there is an edge UV which is in the matching M prime, but it's not there in my core graph. Okay. Well, by construction it means that U has V cover plus 1 neighbors outside the vertex cover. Okay. And now I use this simple result which says that the size of maximum matching or size of any matching is always less than equal to size of any vertex cover. Which means I can find an edge UW such that UW is not matched, such that W is not matched to any other vertex in the graph. Okay. So now what I will do is I will create a new matching in which I delete UV, add UW, and this is also a maximum matching because I have deleted one edge and added one edge. But I claim that M prime is, as I said, it's a maximum matching, but its intersection with the core graph G prime is larger than M prime. And this leads to a contradiction. Why a contradiction? Because remember I said among all the maximum matching in G, let M prime be the one that uses the maximum number of edges of G prime. Okay? So this is my algorithm. I'll construct a core graph G prime of G and compute a 1 plus epsilon 1 plus epsilon by 2 approximate matching in G prime. Okay, so very good matching in G prime. Okay, so let's see what's the size of this core graph. So as you can see in that picture, the size of this core graph, like for each vertex here, there are V cover neighbors in the vertex cover and V cover plus 1 neighbors outside the vertex cover. Okay, so you can see the size of this graph is V cover square. So this is it's either minimum of M or V cover square. But this vertex cover we found by using 3 by 2 approximate matching of Neyman and Solomon, okay, which is always less than the maximum matching. But in this step, I am finding a matching which is 1 plus epsilon by 2 approximate, which means the size of M is always greater than size of M star divided by 1 plus epsilon by 2. So this relation also holds. Okay. So now I'll just do some manipulation. This will imply that the size of vertex cover is less than, so I'll just put M star on this particular thing here. So the size of vertex cover is less than equal to some constant times the size of M. Okay, which means that the size of my core graph, which was V cover square and minimum of M, it is now minimum of M and order M square. Okay. Which means to find the matching in this core graph G, I will take this much time. So now I've gotten rid of this vertex cover and now I have this term M which is sitting there. Okay, is this fine? And this is my complete algorithm. It's one of the simplest algorithm that you can do in dynamic graph algorithm. This is the first thing that you will try. You compute a very good solution and do nothing for next few update steps. Okay, and try to amortize the running time. Okay, so here this is what I am doing. I am calculating a solution which is 1 plus epsilon by 2 approximate. Pretty good solution. And then I will do nothing for rest epsilon and by 2 update steps. Okay, so this is one phase. After this phase, and again find a very good approximate matching, and then again don't do anything for the next epsilon and by 2 update steps. And this is how the algorithm will run in phases. So what about the analysis? So what you have to show is that at each update step, the size of your matching is 1 plus epsilon approximate. Okay, and this is the analysis. Well, at this particular update step, whenever you calculated this approximate matching, your matching is 1 plus epsilon by 2 approximate. Okay, and now since you are doing nothing, well, the size of the matching can increase, but it can increase by 1 at most 1 at each update step. Okay, so your matching reduces by at most 1 with respect to the maximum matching at each update step. Which means that even after epsilon m by 2 update steps, I mean these update steps for which you are doing nothing, the matching is 1 plus epsilon approximate. Right? So you started with very good matching, then it was 1 plus epsilon by 2 approximate, but after these many update steps, it's still 1 plus epsilon. Okay. So what's the running time of this algorithm? So as I said, this algorithm runs in phases. So let's look at one of the phases. So at one particular update step, you found the matching, and suppose the size of that matching is greater than square root of m. Okay. So at that particular update step, you found a matching in that graph. Well, and the time taken to find that matching is minimum of m comma m square, because that was the size of the graph. So minimum of these two is m, because m is greater than square root of m. Okay. So this is the time taken to find the matching. This is where I use Michelian-Gonzalez algorithm. And you did nothing for rest epsilon by 2 m update steps. So I am amortizing this running time over the next epsilon m by 2 update steps. Okay. So if you do the calculation, this is the running time. So this is amortized running time. And the next is when m is less than square root of m. Well, in that case, the size of graph is at most m square. This is what we have proved. Okay. So your running time is, again, this is the time taken to find the maximum matching at that particular update step where you are finding the matching, and after that you did nothing for epsilon by 2 m update steps. Okay. So even in this case, this m and this m cancels out, and since m is less than square root of m, the running time is order square root of epsilon square. Okay. So this tells you that the update time of this algorithm is order square root of m by epsilon square, and you can see this is amortized update time. Okay, because at some update step you are taking a lot of time, and at other update step you are doing actually nothing. Okay, so this gives us a theorem that you can maintain 1 plus epsilon approximate maximum matching in order square root of m by epsilon square update time.
Sir, this is incremental.
This is fully dynamic. Okay. So if you look at any dynamic algorithm for any problem, so connectivity or single source shortest path, there are many parameters that you can actually choose. So one of the parameters is either I'll do it for incremental, decremental, or fully dynamic, or maybe for unweighted or weighted graph. Which is matching, then approximate matching or maximum matching, or you can choose what is the approximation factor. Okay. Randomized or deterministic. So most of the dynamic algorithms that I have seen, they turn out to be randomized because randomization helps. Though the algorithm which I currently showed you, that is deterministic. Okay. And there is a lot of value to de-randomize them. So there are algorithms, randomized algorithm no, but then people try to de-randomize it and find a deterministic algorithm. Other thing is amortized update time and worst case update time. So the algorithm which I showed you has amortized update time. So can you give a worst case update time? That also has a lot of value. And the last is directed and undirected graph. It doesn't apply for matching, but it applies for single source shortest path and multiple shortest path. Now you can see there are many combinations, and that's why you will see many kinds of papers in literature. Okay, for each of these combinations you can see a paper, and techniques would use would be slightly different. Sometimes much different. Okay. So next is fault-tolerant algorithm. So fault-tolerant system continues to perform at a desired level in spite of failures in some of its components. Okay, and most of the systems in real world are fault-tolerant. Okay, you can use Google or your mobile phone. The networks they are fault-tolerant. You want the networks to be fault-tolerant. Now I want to model the fault-tolerant system algorithmically, and there are two models that I know. So one is fault-tolerant subgraph problem. So you are given a graph G, and you want to find the subgraph H of G such that the shortest path from S to all the other vertices are preserved in H. Okay, and I have made this graph. So what is this graph? It's a BFS tree from this. So if you assume this is a undirected and weighted graph, so we'll assume that. So this is a BFS tree. Okay. So now I'll change slightly. So I want to find a subgraph H of G such that the shortest path from S to all the other vertices, avoiding a single edge, they are preserved in H. So for example, if I remove this edge from the graph, then the shortest path from S to this particular vertex, which is this path, it should be preserved in the subgraph. Okay. If I remove this edge, then the shortest path from this particular vertex to this particular vertex, which is then this particular path, it should be preserved in the graph. Okay. And now it's not clear what should be the size of this subgraph. Okay. You may be thinking that you may add all the edges from G to H. Okay. But this is the result by Carter and Feller. They showed that ordered 3/2 edges are both sufficient and necessary. So it's theta n by 2, right, and n is to 3/2. Okay, so we'll require at least these many edges. And they give a construction in which order n is to 3/2 is. Okay. There is one more problem which is called fault-tolerant algorithm.
You're looking for a subgraph.
Yeah, you are looking for a subgraph.
So what if G doesn't even have that many edges?
Yes. So if G does not have that many edges, then they will just put all the edges from G. Okay, but they show a subgraph. They show a graph in which these many edges will be required. Okay. So another is fault-tolerant algorithm. So you have an input, and we always assume that input is a graph. And what we want to make a data structure from this input. So pre-process the input to weight a data structure, and this pre-processing will be free. after we have made this data structure, some queries can come. Okay, so there is this query algorithm which will consult your data structure. So you have to design a query algorithm which will use the data structure to answer queries efficiently. So what can the queries can be? I mean, so given a graph G, you have to design a data structure that can answer the following query. And let's assume the query is find the length of shortest path from a source to a vertex P, where V can be any vertex. Okay. So what kind of data structure can you design here? What would be a simple data structure? So what you can do is we can just store distances from S to all the other vertices, right? It takes just order n space, and you can then answer queries in order runtime. It's a pretty simple. Just store the distances from S to all the other vertices. But now, suppose I change this problem slightly. So given an undirected unrelated graph G, you have to design a data structure that can find the shortest path from a source S to any destination, avoiding a single edge. So we have to avoid a single edge. Formally, the query algorithm should answer the following question quickly. So this is query STE, where this source S is fixed. P can vary, and then there are many edges that you want to avoid. So you want to find the length of shortest path from S to T, avoiding this edge P. Such a data structure and the query algorithm is also not indispensable. Okay. So now it's not clear what's the space and what's the time that you have to take. I mean, and you can see actually we can use this particular result. So this result, actually I can make a graph of size n raised to 3 by 2 using this result. Then whenever a query comes, what I'll do is I will delete the edge from this graph and then do a BFS. So the space taken is order n raised to 3 by 2 and the query time is the size of this graph because we are doing a BFS. It's again order n raised to 3 by 2. So there exists an algorithm in which the space taken is order n raised to 3 by 2, the query time is order n raised to 3 by 2. Below et al, they had another algorithm where the space taken was order n raised to 3 by 2, but the query time was order square root of n. Okay. Recently, we had this result in which we present a distance array which size is order n raised to 3 by 2. So there is this tilde notation which hides log n factors. So the space is order n raised to 3 by 2 and it can answer queries in polynomial time. Okay. So this is how we will solve this problem. So initially what we will do is we will sample the set of terminals of order square root n vertices. So each vertex is sampled with probability 1 by square root of n. And now I claim that if you look at any ST path which is sufficiently long, with high probability on any ST path there will exist a vertex TS such that the length of the path TST is order square root of n. So this particular length is roughly order square root of n log n. This height is log. So with very high probability you will find this TS. Okay, this TS is the sample vertex. Okay. And now there are two cases that you have to check. Well, look, you have a query. You have a query algorithm, and in that query algorithm, well, you want to avoid an edge which might be on TST path or STS path. Okay. So any query can come, and the edge that you want to avoid might be in TST or STS. So this is called the near case, and this is called the far case. So let's look at the near case, when the edge is on TST path. So what I will do is the following. I will store all the replacement paths avoiding edges in the path TST. And the number of shortest paths stored, well, because the size of TST is roughly order square root of n, well, the number of shortest path that I am storing is roughly order square root of n. Okay. Again, I just want to say this, I am not storing the actual path, I am just storing the length of the path. Okay. That's why the number of shortest path that I am storing is order square root of n. Which means that the size of the data structure for a fixed T is order square root of n. So whenever a query comes and this edge is here, I will just consult this data structure. Okay, so for a fixed T, the size of this data structure is order square root of n, which means that the total size of this data structure is order n is to 3. So this is the easy case. Now let's look at the next case, which is the far case, which means the edge exists on STS path. Okay, and now I claim that the replacement path might look like this. So it might pass through this particular vertex TS, or it may avoid the vertex TS. Okay, so let's look at the easiest part. So let's assume that the replacement path passes through TS. Well, what I'll do is I'll store the length of all the shortest path from S to TS, avoiding each edge on STS path. So for this particular edge, I will store the length of shortest path from S to TS, avoiding E. Okay, and the space taken by this data structure is the number of terminals into the number of edges on STS path. So the number of terminals is order square root of n, and the number of edges on STS path is n. So this is again n is to 3 by 2. And then I have to also find a path from TS to T. Okay, so what my plan is, if the replacement path passes through TS, then I will find the shortest path from S to TS, avoiding E, and then I will add the shortest path from TS to T. In which case I want to find the shortest path from TS to T, I'll store it somewhere. So I will store the length of shortest path from each terminal to each other vertex. Again, there are order square root n terminals and order n vertices, so this data structure is also n is to 3 by 2. And this is the final case, and this is actually the hardest case for us. What if the replacement paths, so these are all replacement paths, and these are avoiding TS2. Okay, so these replacement paths are avoiding edges on STS path, but they are avoiding TS2. And this is the main technical result of this paper. It says that the total number of replacement paths from S to TS that avoid from S to T that avoid TS2 is order square root of n. So just look at this particular result. There can be many edges on STS path. Okay, and my aim is to find the replacement path for all these edges. Okay. But what I am claiming is that the total number of replacement paths from S to TS which avoid TS2, it is just square root of n. So it's not very high. I mean, you may think that there might be n such replacement paths here, but it is just square root of n. If this is true, then what I can do is I can make a binary search data structure for all these replacement paths. So here is this path P1, and it is avoiding all the edges from A1 to A2. So this is here. Similarly, this is path P2, and this is avoiding all the edges from A2 to A3, and this is here. So I will make a binary search tree kind of data structure which will help me in the query idea. So, but I will not go into this particular data structure. Well, the size of this data structure is order square root of n because these are the number of paths by that particular number. Well, this implies the total size of the data structure is order n is to 3 by 2. And this will give you the theorem, but in the rest of the talk, this is what I will prove. So I will try to prove that the total number of replacement paths from S to T that avoid TS2 is order square root of n. So let's look at some basic observation first. So suppose P1 is a path which avoids this edge E1 and it avoids TS2, and P2 is a path which avoids E2 but it is avoiding TS2. So is this picture correct? Can these two replacement paths exist? So I claim that the answer is no, because look, if P1, the length of P1 is less than the length of P2, then well, the replacement path that avoids E2 is P1. Right? I can use actually P1. Why should I use P2? So which means the picture should look something like this. So this P2, the replacement path P2, it should start. I mean, this is called the D2. So I will define it formally in 2 slides. This P2 should start after E1. So this is the property P1 that the lower replacement path will pass through the edge which is avoided by the upper replacement path. So this is the upper replacement path, this is the lower replacement path. So the lower replacement path should pass through the edge avoided by the upper replacement path. So this, I know this is the picture. Let me ask you another question. Can the length of P2 be greater than the length of P2? So this length is greater than this length. Well, again the answer is no, because if the length of P2 is greater than equal to the length of P1, well then the replacement path which can avoid E2 is actually P1, because its length is less than the length of P2. Right? Which gives us the second property, that the lower replacement path has length which is strictly less than the upper replacement path. So this is the upper replacement path, this is the lower replacement path, and this length of this replacement path is strictly less than this. That is why we will use this. Why would we use this? We will just use this, because this is also avoiding it. Which basically means that the length of all these paths are distinct. It's just a nice correlation. And now let me define detour. So look, I want to find replacement path that avoid this edge E. So they have to somewhere bounce off from this original ST path. Okay, and then again come back. Okay, so my detour is exactly this green path, or formally it is P minus set minus ST. Okay, so the point from where it comes off from the original path ST to the point it finally merges. Okay, so now what I will do is the following. I will try to associate square root and first what I will do is I will process all the replacement paths from top to bottom. Okay, all these replacement paths are avoiding TS2. And what I will do is I will try to associate square root and unique vertices on the detour of these replacement paths. Okay. So suppose I look at the first path which is suppose P1, and I see that the number of vertices here is greater than square root of n. Then I will associate these square root vertices with P1. Next is maybe this. So this is my next replacement path. Okay. Again I see that the number of vertices here is greater than square root of n. Well, I will associate the vertices here with this replacement path which is P2. My next replacement path is this, which is P3. Well, I have already associated vertices from this path to P2. So I cannot associate vertices here, but let's look at this particular orange path. Okay. Now suppose that the number of vertices on this orange path is greater than equal to square root of n. Okay. Then I will associate them with P3. Okay. So these are basically good events for us. Okay, in which we are able to associate square root and vertices with each replacement path. If only good events happen, then can you see there will be only square root of n such replacement paths. So the problem is when a bad event occurs. Okay. So let's go to the next slide. Suppose this bad event occurs. So I had associated square root and vertices with P1, and now when I see this orange path, well, the number of vertices on this orange path is less than square root of n. Okay. So the size of BC is less than square root of n. Well, remember this path P1 is SA, then AC, then CD, then DT. Okay. I claim that there is another path from S to T that avoids E1. So this path P1 is avoiding E1. Can you see that path? It is SA, then AC, then CD, then DT. Okay. Well, I will not go why it is a valid path avoiding E1, so I will just skip this part. From the picture it is clear, but you have to prove that this is a path which avoids E1 too. Okay. So I will not go into this. But why did our algorithm not choose this path, but it chose this path? Well, our algorithm chose this path because the length of P1 should be less than equal to the length of this path. Okay. Right. So the length of this path should be greater than equal to the length of P1. That is the only reason our algorithm chose P1 and not this path. Okay. So now this is what I will do. I mean, this is the length of P1, and this is the alternative path. This is SA, then AC, CD, then DT. And this length is less than this length. Well, I will remove SA and AC from both sides. So you get CD plus DT is less than CD plus BT, and add BC in both sides. And now remember, length of BC is less than square root of n. This is where I started with. Which means BC plus CD plus BT is 2 square root of n plus BT. Okay. So now where are we going? So let's look back. Okay. So on the left hand side, I claim that we have a replacement path from B to T avoiding E2. Okay. So this is BC, then CD, then DT. So this BC, CD, and DT. This avoids E2. Okay. And a good property about this particular replacement path is that its length is just 2 square root n away or greater than BT. Okay. So it is very, very close to BT. We will try to use this property. Okay. So this is where we were. So we had processed all the replacement paths which are above P, and some replacement paths are still left, and we are stuck at this particular replacement path P. Okay. And then we see that BC is less than square root of n. So we are stuck here. Well, by property P1, all these lower replacement paths pass through the edge avoided by P. This is what we had proved. This was a property P1. Well, then we can assume that all these replacement paths, they actually start from P, because all these replacement paths will pass through P. So this is what I do. I mean, let's just break off ST. Okay. So I'll assume that all these replacement paths start from B. And by property P2, the lower replacement paths have length strictly less than the upper replacement path. Okay. So these lower replacement paths, their length is strictly less than the length of P. And the corollary of P2 said that all the replacement paths have distinct lengths. And this is the last line. Well, I know that the length of this replacement path will strictly lie in this range, BT and BT plus 2 square root of n. Why BT? Because the length of this path is BT itself. Why BT plus square root of n? Well, this is what we proved here. The length of P is less than equal to BT plus 2 square root of n. Okay? And all these replacement paths would have length less than the length of P. But the length of P itself is less than BT plus 2 square root of n. And now you can see that the number of, there are only square root n numbers in this range. Which means there are only square root n paths to follow. Okay? Which means that the total number of replacement paths from S to P, which avoid PS2, is just order square root n. Okay? So this is the main result of this particular paper, and we extend this result even to multiple sources, though the extension is slightly technical, but it uses whatever we have done in this class. And there are many open problems. One of the open problem is what happens when we have two faults. It's actually not very easy. It involves a lot of case analysis. In general, what will happen if there are k exceptions? Okay. What happens when you want to, when there is there is no single source, but there are, all the vertices are sources, so all pressure response. So this is all I have. Thanks. So in the directed setting, so the main thing, the main point of this result is that your size of graph is substantially less than the original graph, or the size of the data structure is n^3/2. So in the directed setting, it's not clear that you can get anything. If you can come up with cases where you will require order n space. Okay, but even in order n space, can you do order 1 query time? Because the query time is also very important. Okay, that I am not sure. Okay, so the thing is, what is the running time of this algorithm? So as I said, the pre-processing is free. So you use any algorithm, any polynomial time running algorithm.
So the NISER 3x2 load on is that there are graphs produced
No, so there is a graph.
But for specific graphs, for your input graph, you may be able to.
Yes,
smaller
yes,
size.
yes, yes. Yeah, so there will be then, yeah, so there is a, yeah, so there is a log and approximation. So you are saying there may be a graph in which the subgraph would be of very less size, right?
Even for any given input, so for your graph, you have a subgraph which has size equal to you can answer in constant time.
Yes.
Okay, for the graph, that graph you may be able to even have a subgraph with fewer edges.
Yes, so that's what she's saying. There are log and approximations.
Which means
If the size of subgraph is suppose x, then the size of your subgraph is x into x.
that's the optimum subgraph.
Optimal subgraph is x, then the size of the subgraph that you will output is x log n. But this is the subgraph model, not